Today we're going to see the implementation of the finite element methods on the computer. How do we actually solve the problem? We have looked at this point up to now at the ability of being able to apply the Galerkin's method to obtain a set of equations that actually solve the partial differential equation problem. That set of equations has this form. Like the form says a stiffness matrix times the vector of nodal value equals the vector of loads or constants in here. So the objective of my explanation at this point is to find the value of nodal values once the global stiffness matrix has been found for the region. So we have applied the Galerkin's method and applied all the basic coefficients that we need to calculate based on the coordinates, and finally come up with this set of equations. So this one is the stiffness matrix right here. This is the vector of nodal values, and these are the loads. So find phi, that's the problem. So we have found the global stiffness matrix from the individual stiffness matrices. So now we evaluate each individual stiffness matrix, and then we put it into this form. This is what this means. The summation of all the individual finite element matrices is the global stiffness matrix. Okay. In this case, you have a region in here, as you can see. You have a piece of 1, 2, 3, 4, 5, 6 nodes, and you have the dimensions in here. The idea here is that we can write an equation for the solution of any element. In this case, element number 3, this one. Yeah. You see, element number 3, if we write this equation in terms of all the nodes, only 3 of those would have values, because for this triangle element, only phi sub 2, phi sub 5, and phi sub 4 will have nodal values. But for this element, all these other ones that are on the periphery are not going to have a contribution to the solution. So for element number 3, you see here, we have 0 phi 1 plus the shape function n2 that belongs to element number 3. So that is related to phi sub 2 plus 0 phi sub 3, because phi sub 3 is over here. This is 0. And then of course on F4 you are going to have n sub 4 that belongs to element number 3 times the nodal value phi sub 4, and then n sub 5 that belongs to element number 3 times phi sub 5 plus 0 phi sub 6, because phi sub 6 is over here, completely unrelated to this. So if we eliminate this and contracting, we will find this equation that applies to element number 3. In any case, this is what the whole Galerkin's theory, the application of all Galerkin's theory, where it leads us. It leads us to the solution phi over the finite element number 3 is a linear combination of the shape functions and the nodal values. In this case, 3 shape functions, 3 nodal values. If you put together the stiffness matrix using the individual matrices of the elements, this is what you will see. Like in this case, we have 4, 5, and 4. This is the stiffness matrix for the that element. Okay. And so if you, this is 2, 5, and 4, if you put it into the global stiffness matrix, see what happens? 2, 5, and 4 will, those numbers will fit in here. But we have to follow the numbering system. So this element 2, 2 here is going to be element 2, 2 in the global stiffness matrix, see? 2, 2. This one over here, this is element 3, 1, no, 1, 3. So then you will have the element, see, 1, 3, but the 1, 3 on this matrix, but in reality the index is 4, 2. So here's 4, 2. In here, 4, 2. And then you have that element 4, 2 minus 1/2. You have 5, 5 is 1/2. So 5 here and 5 over here is this. This one, for example, is that one is that this one here is 5, 2. So in the global stiffness matrix, no, here. 5, 2 is the 0, right? So in here 2 is going to be 5, and then 2 here, see? So you this global stiffness matrix is populated by the contributions of each of the individual stiffness matrices, and then in some cases the elements get superimposed from one element to the next, and that indicates simply that the whole region is together. Okay, so the global stiffness matrix for element number 3 would be put in the into this global stiffness matrix. What I'm trying to say is the stiffness matrix of element number 3 can be put in the global stiffness matrix like you see in the picture here. Okay, so that's that. And then once we have a system of linear equations of this form, as indicated before, k times being the stiffness matrix times the nodal values equals the vector of loads. Okay, so this form, we try to optimize it so that it would be easier to create the inverse, because as we have seen in here, how are we going to solve this? The way we're going to do this is by multiplying by the inverse on both sides and then simplifying it a little bit. So in here you have this, for example here, I would do this something is funny here. Well, we'll see. Red pen. You have in here that this is okay. For some reason my mouse and the screen are out of phase. I don't know if I'm gonna be able to do it. See the way it's doing it is writing outside, and I don't understand why. So we're not gonna do this. We'll just keep the explanation there. So in here, if you populate this global stiffness matrix, chances are you're going to create this kind of matrix, or at least the numbering systems or the program is going to try to create a set of matrices where the so-called bandwidth is small. The smaller this bandwidth, the faster you can solve you can invert the matrix. So what I'm trying to say is the global stiffness matrix that we generated over here may be manipulated or arranged so that values don't change, value of the solution don't change, but what they will change is the number of elements that are away from the diagonal. Like if you have one element that is way off by itself, that something is funny with that system. Most of them will will come up like this, where you have a diagonal and there are alternate terms on both sides. But even those terms should be minimized to the minimum number of terms, so that the zeros, on the other hand, we want more zeros. The reason we want more zeros is because it will simplify tremendously the calculation. Because the smaller that we have the bandwidth, the faster the computer can invert them. So the property is in this case that matrix K is symmetrical, that is also positive definite, and then the characteristics of K, we want to be able to reduce the storage space requirements, mainly because if you have like a 4 by 4, you calculate 16 determinants 4 by 4, 16 minors. No, 16 minors 3 by 3. And if you do a 5 by 5, you have 25 4 by 4 determinants to deal with. So that's what we want to reduce storage spaces. Just some notes about the modified system must give the same answer, and the size of K and F should not change. Why the dimensions of K should not change? Dimensions of K should not change because if it does, it means somehow more nodal values appear, and that can be, right? So here's an example on the equations. On if you take 3 at a time like this for all five elements, you will have a situation where you can clearly see is a bandwidth is developed over here on both sides. We would like to see more zeros, but these ones are good to solve the problem. So you have in here that with phi sub I equals 150 and phi sub I 40, modify the system. So we need to do that, modify the system. Step number 1, set the coefficients in row 1 to 5 equals to 0, except for the coefficients in the primary diagonal. Okay. Step number 2, you replace those values on the first and the nodal values on the first and the last equation, because those nodal values are part of the boundary value problem, which finite elements are. And this is possible because phi sub I is known. The coefficients of phi sub 2 through phi sub 3 should be 0. Sum is true for phi sub 5. Conclusion solution of A, the solution for the nodal values. We need to pursue that. So since phi sub 1 and phi sub 5 are known, then the terms of F need to be modified. In other words, in the other equation, by subtraction of the known quantities associated with the coefficients phi sub 1 and phi sub 5. So at this point, it's an algebra problem. We substitute this one, just this and this, and the value of phi sub 5, which is, we also know. And then the value of the equations. Okay. Solution of the finite element equations. You can have a so-called Gaussian elimination method, or there is a inversion as I outlined for you. But in this case, if you use the Gaussian elimination method, you decompose K into upper triangular matrix. The column vectors are modified and obtain a solution using backward substitution. So here's what will happen. Example, if we have this global stiffness matrix, nodal values and quantities, loads, you can see. This needs to be transformed into one like this, so that phi sub 4, phi sub 3, phi sub 2, phi sub 1 can be found by substituting. Okay, so this is how the Gauss-Jordan elimination method works, by using the principles of adding two rows, or multiplying one side and the other for one element. It all works towards this goal. In the last, you're building a triangular matrix. The triangular matrix, if you know phi sub 4, if you know D, and you know where E44 is in X and Y, you can find out the solution for phi sub 4, but also you can find a solution for phi sub 1. So always keep this in mind. It is a boundary value problem. So in every finite element problem, they give you the boundary conditions or points, whatever is. In this is we want to do this, and the last equation, when it's like this, you can see phi sub 4 is D4 divided by A44. And then once you know that, substitute in the next equation those two variables, Once we do that, those three variables are substituted in the one above until we find all the values of p sub 1 to p sub n. Okay? Any questions about this? No? Okay. So this is the way we obtain the solution by Gauss-Jordan elimination method. You'll have this. You have this triangular matrix. You will convert it into a triangular matrix in such a way that the last value, when you see here, the last value of e sub 4 can be found from this equation. And when this is found, you substitute on this and then on this and this until you find all of them. That's how this works. And computer can implement the Gauss-Jordan elimination method or the matrix inversion. Chances are that what we're doing is a pure matrix inversion problem. And most softwares are going to do that. Most software programs are going to do that.